Hey, Peakemsters, this is Mrs. Vanderwalle bringing you another edition of Blankwalle. This is still section or chapter 15, section 6. This is now part 3. So we left off seeing how we deal with weak acids. Sometimes the approximation will be wonderful. Sometimes you're going to have to use the quadratic. Bummer. All right, so let's continue on here. It says the initial concentration in the K's of several weak acids are listed below. For which of these of the X is small, approximation is least likely to work, and find the pH of the solution. All right, well, I think you can probably cancel out 2 of them. So then which one is probably least likely? So go ahead and take your pick. I don't think it's A. Why not? Because it's 10 to the negative 5th. I don't think it's B because it's 10 to the negative 6. So it's either between C or D. All right. So which one do you think that 5% is going to be worse? It's probably going to be letter C. All right. When you have a smaller initial value, that 5% rule is going to be a little bit more iffy, all right? If you have a larger one, then it may work out for you, okay? So letter C is probably the one that's least likely to work for you, okay? So part 4, you're going to do the reverse. What if I give you the pH of this unknown acid or something, all right? And I'm asking you to find the Ka. We are doing the reverse, okay? So what does pH stand for? All right, so what is pH? pH is the negative log of H plus concentration. So how can I use this to help me? If I know what pH is, what can I solve for? Well, if you said H plus, you're right. So what do I need to do to solve for H plus? What's in a sense the opposite of a log? It's 10 to the power, isn't it? 10 to what power? Negative pH, okay? And by the way, a little side note here, what does pH even stand for? It stands for power of hydrogen. Not like strength, like, you know, muscle man or anything. It means power. Well, what's another word for power is exponent. So that pH is an exponent, power of hydrogen. And it has to be a negative pH, all right? So if I know pH, I can find H plus. And if I know H plus, I can solve for Ka, can't I, all right? So let's look at problem number 27, all right? So what do you think is the first thing we need to do? Well, I bet the first thing we do is set up you got it, the ice table, all right? So here we do this, and here we're going to subtract x from both sides, all right? And then add x to both, well, you know, subtract x here, add x here, and then here we go, all right? Now, I don't know what my Ka is. That's what I'm trying to solve for, isn't it? But wait a minute. What is my my term now? Isn't this my term? How am I going to find x? How am I going to find H plus? I'm going to do this. And that's what's going to get me there, all right? So here we go. I guess I'm going to squish it up over here. I'll move this over a little bit. All right, so look at this. 10 to the negative 4.25 is 0.0000562. That is H plus. So what can I do with this number now? If that's what my H plus is, well, guess what? That's what my A minus is too. All right, they're the same number, aren't they? And what can I then do? I can subtract, oopsies, I can subtract from the initial concentration and get this. All right, now what is 0.0000562 equal to? 3.15 times 10 to the negative 9. Now, what about my denominator? If I were to do this out, I'd probably get 0.099999, like 438, all right? What's 0.099999? Awfully close to. Oh, 0.1. All right, so what does this mean? Do you think I could maybe get rid of that term? I bet I could, all right, because it's essentially the same number. So what does this mean? That's my Ka value, 3.15 times 10 to the negative 8th. And does it make sense why I canceled this out? Look at my value, 10 to the negative 8th. All right, I bet I couldn't cancel this out if this were actually a much larger number, could I? All right, so let's see what problem 28 is. All right, a 0.175 molar solution of HA has a pH of 3.25. Find the Ka for this acid. Why don't you work on this? So pause this, do it, and only when you're done, come back and see how you did, all right? So go ahead and pause this. All right, how'd you do? Well, let's see. All right, here is my setup. All right, so again, what is my pH? pH is negative log of H plus. Oh, so I can solve H plus by doing this. Here's what H plus is, 0.000562, all right? So I plug in the numbers here, and look what this is. Now, this is a little bit closer to the problem before, all right? With 3 sig figs, my number did change a little bit. So I'm going to use the 0.174. So I'm not going to cancel this out, all right? So I get 3.05 times 10 to the negative 7th over 0.174, and I get 1.82 times 10 to the negative 6. So this is getting a little bit closer to that cutoff point. I bet if I left this as 0.175, I probably get the same answer anyway. But, you know, better be safe than sorry. That's how I look at it. All right, let's go on. So this next topic in this very long section is percent ionization of a weak acid, all right? So whenever you hear the word percent, think of part over whole, all right? So the percent ionization is the amount dissociated over what? Oh, this is important, folks. Over what the initial, here, I'm gonna highlight this for you, all right? You want the initial amount. That's your whole. That's what you started off with. So what is my numerator? This is your X from the ice tables, all right? So when you solve for the H plus or the H3O plus, that's your X. So it's X over initial, part over whole, okay? Try to learn this, try to memorize it, all right? So it says the equilibrium of H plus of weak acid increases with increase in initial concentration of the acid, okay? So for a given weak acid, the percent ionization increases as the acid becomes more dilute. Let me pause here and kind of bring you back to something real quick, okay? Do you remember the very, very opening statement of section 15.6? I don't know, it was 2 videos ago, all right? So we started off and I said, what is the effect of adding H plus to the water according to Le Chatelier? What did we say? It shifts to the right. So if I'm going to add water to a weak acid, aren't I diluting it? And what's going to happen is going to shift to the right. And what's going to happen, I'm going to make more H plus. Let's see how this works. All right, so going back to that again. So for a given weak acid, the percent ionization increases as the acid becomes more dilute. And I'm adding more water to it, correct? So if it is becoming more dilute, I'm adding more water, I am shifting the equilibrium to the right, I'm making my numerator actually bigger now. Okay, so that's the effect of Le Chatelier here. So maybe that's a way to think about this. So as your initial concentration goes down, your percent ionization goes up. Okay, the reverse is also true. The percent ionization of a weak acid decreases with what? Increasing concentration of the acid. Okay, so maybe that puts things into perspective. Okay, so let's do problem number 29. All right, so it says calculate the percent dissociation of acetic acid in each of the following solutions. So I will start off with a 1 molar, all right? Notice how I start off my ice table every single time. So don't be lazy, always do an ice table, okay? And now what? All right, we need to solve for what the H plus is. We need to figure out what X is, okay? Because that will be then my numerator for the percent dissociation. So here's this. All right, and so now I have x squared over 1. Remember, this is 10 to the negative fifth, so what do I essentially do here? I essentially, let's here do this, get rid of this term, don't I? Okay, because this number, 10 to the negative fifth, I'm pretty certain I can make that assumption, all right? So it's not 1.00 minus x, I'm going to assume it's 1.00, okay? So now what? I'm going to multiply both sides by 1. My number didn't change. And then I'm going to take the square root. And so what do you get? If you got this number, you're right. So now what do I do with this number? Let me scroll down. All right, so my percent dissociation equals part over whole. What's my part? H plus. What's my whole? It's the HA with a little I, initial. So what is my H? That's what I just solved for over here. That's what my X is. What is my initial concentration? It is 1 times 100%. If you do the math, you get this, okay? So what do you get if you have a 0.1 molar, okay? Why don't you pause this, you do it, and when you're done, come back, okay? Sounds like a plan. Go for it. All right, let's see how he did. Well, there's my ice table. There is my setup. All right. There is, I left, notice I didn't, put all my intermediate steps. So x squared equals 1.8 times 10 to the negative 6. Take the square root. What do I now do with this x? Okay. Well, my percent dissociation is the h that you just solved for, divided by my HA initial, okay, that's 0.1, all right, so I get 0.134 or 1.34% dissociation, all right, what was it over here? 0.424%, this is 1.34, so notice this is exactly, the math is backing up what we said before. The more dilute you have, the higher percent ionization, all right? So that's our conclusion. The lower the initial concentration, the greater the percent ionization, all right? Hopefully that makes sense to you. All right, so let's go to the next page, see what's coming up. All right, so which of these weak acid solutions has the greatest percent ionization? Which one has the lowest or most acidic pH? Okay, go for it. Okie dokies. So which one's going to have the greatest percent ionization? Well, it's the one that has the lowest molarity, isn't it? So which one has the lowest or most acidic pH? Well, it's not going to be letter C. That one has the lowest initial concentration. Think back to what we did earlier. I think it was, I forgot which one, nitrous acid? I forgot. Anyway, it's the one with the highest initial concentration. So that's your answer for the second half, all right? All righty, row. So problem number 31, this is the opposite of what we did before, okay? So now I'm telling you what the percent dissociation is. Now you're going to find the Ka for this value. So wait a minute, isn't this a lot like if I give you the pH what the Ka is? It sure is. You can find X using this value again, okay? So maybe you can reason this out, and when you're done, come back. All right, so how do we do? Well, guess what you do first, all right? I bet you set up your ice table first, didn't you? All right, that's what I did. Here is my ice table, and I'm solving for Ka, right? Well, I need to know what X is, don't I? Okay, well, this one doesn't tell me. If I keep going, I can figure out what X is, isn't it? So if I know the percent dissociation equals 3.7% equals X over 0.1, my initial times 100%, well, what did I do? I first divided both sides by 100%. So this is 3.7 divided by 100, which is 0.037. Then I multiplied it by 0.1 to get 0.0037. That's my X. That's my X. So now I can plug it in, and I went ahead and used that value. I didn't assume anything, all right, because 0.1 and 0.0037 isn't that far apart from each other. And I plugged this in. I got 0.00014, so that's my Ka. All right, we got one more topic to cover in this section. This is the section that never ends. And so I'm going to have to tell you once again, don't wait to be great, and we'll see you shortly for what I am positive will be the part 4 and the last part for section 15.6. All right, see you soon. Bye-bye.